So the last thing we're going to do today is we're going to walk through another case study. This is case study ex2. And this case study shows how you can use the Java Executors and Executor Service features to support structured concurrency to create a new virtual thread per task. And it also shows how you can combine Java streams, in particular Java sequential streams, with these new structured concurrency features, which I tend to like to do because I can't stand writing classic Java. It's horrible now. The tasks in this case study are all CPU bound. We'll look at some other examples that are IO bound later. So here we are in the ex2 project in my Loom folder in my live lessons repository. And we can open this up and you'll see the example. This example shows the Java Executors, Executor Service variant of structured concurrency. And to run this example, you need to have really modern Java, Java 19 or later, with Gradle version 7.6 or higher. So here's what this example does. It's going to parse some command line arguments to tell it certain things like how many elements we want to have. As you can see, we don't really have any arguments except we're saying enable preview features in Java. So it's going to use the defaults, which are set in this options singleton. We're then going to generate a bunch of random integers. And you can see here how this works. This is kind of what we did before. We generate a bunch of integers within a range. We box them and return them as a list. No surprise there. And then we're going to run some tests. And these tests are really fun. What they're going to do is they're going to use Java's structured concurrency via the executor service mechanism of a new virtual thread per task executor in order to go ahead and check the random integers to see which ones are prime or not prime. That's one thing it's going to do. And then in parallel to that, we're also going to go ahead and compute the greatest common divisor for those pairs of those random integers as well. So we're going to do those two things in parallel. And the way we do this with the executor service approach is we define a couple of local variables here, one called prime check futures, the other called GCD compute futures, which are futures to lists of futures to either prime result or GCD result objects. We'll talk about those in a second. Then we come down here and we use this try with resources block to make ourselves a new executor variable that's bounded within this try with resources scope. We initialize that with the executor's new virtual thread per task executor factory method, which gets us one of these things that we need to be able to fork stuff. And then we go ahead and we say executor, which is that var, submit a call to a method called check primalities. And it'll check the random integers to see which ones are prime. In parallel, we also submit another call to another method called compute GCDs, which takes the same parameter list and computes the greatest common divisor for pairs of those integers. So these two calls go in parallel. Notice executor submit is the means by which we say create a new thread. And we'll look at those methods in a second. However, let me show you what happens here. These things go off and run in parallel, and this block of code does not exit until both those calls are done. When those calls have finished, we're now going to go ahead and print the results. So even though we have futures, a future is this proxy to a computation that's running asynchronously. By the time we exit that scope, by the time that closed curly brace was hit up here, right there, the futures are all finished. We know they're done. We wouldn't have exited if they weren't finished. So what we do now is we say prime check futures dot result now, which just says, I know this is a future, but I know it's done. Get me the results, which comes back as a list. And for each of the elements in that list, go ahead and print out the result, which in this case is going to be the results of prime checks. And over here, down here, we're going to do the same thing, but with the results of the GCD computations. So these go ahead and print the results. Now, what's interesting about this particular example is that both of these calls, check primalities and compute GCDs, in turn use structured concurrency. So we're doing structured concurrency nested. At the outermost level, we're checking the primalities concurrently with checking the GCDs at a high level. And then within each of those calls, we're then going to do all the computations in parallel as well. So let's take a look at an example. Here's check primalities. Check primalities takes a list of integers, and it returns a list to futures to prime results. And it has a nested try with resources block. So it's nested inside the one that is doing the 2 computations at the outermost level. So once again, we make ourselves a new executor that's a new virtual thread per task executor. Except now what we're going to do is we're going to take that list of integers we had, passed as a parameter up here, this guy, and we're going to stream it. We're going to turn it into a stream of integers. And then we're going to apply the map transforming operation, which is this intermediate operation that transforms things. And what it's going to do is for each integer, which we call prime candidate, for each prime candidate, we're going to go check the primality of that prime candidate concurrently. And we'll see what that method does. I wrote that method called check primality. We'll look at it in a second. That's going to return a future to a prime result. Each call to check primality returns a future to a prime result. So we have a stream of futures to prime results, which we then collect into a list. So we end up with a list of futures to prime results. That's what gets returned. And by the time we return, all of those computations will be done. So even though they're represented as futures, they're all finished or completed futures. So let's go take a look at check primality. Here's check primality. Check primality is just a good old method that takes the prime candidate we want to consider whether it's prime or not, the executor service, which is the one we just saw, that's the new virtual thread per task executor, and it says, hey, executor, please submit this lambda expression to run concurrently. Please submit this task. And what that does is it checks to see if the prime candidate is prime, using the effectively final features we talked about before, prints out the results, and then whatever the results are, we create a new record type called prime result, which stores the prime candidate and the result of checking to see whether the thing is prime. This is what a record looks like. This is also a modern Java feature, a really modern Java feature. So prime result is a record which contains a field called prime candidate and a second field called smallest factor. And unlike Java objects, which contain extra stuff like a virtual pointer, an intrinsic lock, an intrinsic condition, and so on, a Java record only contains the field contents. So it's basically a data holder. It's what's sometimes called plain old data, or a pod. Sometimes called a plain old Java object. I guess it's not a pod, it's a pod. It's plain old data. And so that's what gets returned there. So that's check primality. And then you can see down here we have compute GCDs. And since we have a few minutes, let's kind of walk through that, because this is a fun example too. So this example looks very much the same as the one we had before. We pass in a list of integers. We create ourselves this executor that will be a new virtual thread per task executor. But now we're going to do something a little different. What we're going to do is we're going to take that list of integers and we're going to call a class I wrote called list splitterator. And what this is going to do is it's going to go through the list of integers, and for each adjacent pair, it's going to go ahead and split that into a stream of 2-element integer arrays, one for each adjacent pair. So we're going to end up having basically a stream of 2-element integer arrays. And we'll take a look at how splitterator works in a second. And we're then going to take those 2-element integer arrays, and we're going to call compute GCD on each of those things, passing in the executor. And then we're going to end up with a list of futures to things called GCD results. And we'll look at that in a second. So let's go ahead and take a look at list splitterator first. So list splitterator. Splitterator is a feature that was added to Java 8, and it's used with Java streams, and it's used to split something that's non-stream oriented into a stream. So in this case, we're going to be splitting into a 2-element integer array. And you can see that we have a local field called mints, which is the list of integer array objects to process. We have something that keeps track of where we are in the processing. And this is what the code looks like. There's a method called try_advance that's called automatically by the streams framework. And it checks to see whether or not we've reached the end. If we have not reached the end, we go ahead and get the indexed item and the indexed +1 item, and we make a new 2-element integer array that contains those values. We store it in the parameter that's passed in here, and then we increment the index field by 2, because we're skipping over the 2 elements we just created an integer array from. and we say keep going. And we keep doing that until we've reached the end. So this little piece of code will basically create for us a stream of 2-element arrays, and then compute GCD takes those parameters, and you can see what it does is it goes ahead and uses executor submit, which creates a virtual thread in the background, and it computes the GCD of integer sub 0 and integer sub 1, and then it prints the results, and then it creates a new GCD result, which has integer sub 0, integer sub 1, and the result. And as you might expect, GCD result is also a record which has a first field and a second field and this GCD result. So that's just kind of fun with streams, but the real point here is we're doing these computations in the background, so we end up with a future to a GCD result. Here we end up with a stream of futures to GCD results, which we turn into a list. So we end up with a list of futures to GCD results that come back to this call. So armed with all that knowledge, let's go ahead and compile and run the program. And what it's going to do is it's going to basically submit 2 virtual threads, one of which will do the primes, one of which will do the GCDs. Each of them, in turn, will turn around and do a bunch of virtual threads using the executor's executor service mechanism. And here's the results. This is what's printed as we go along. These calls here are the ones that are doing prime checks. These are the ones that are doing GCD computations. And then here's the final results. You can see that we print out the prime results with the prime candidate and the smallest factor. And here's the GCD results as well. Don't get too wrapped around the axle with the examples. They're really just there to do computation in parallel, showing off the cool features of Java structured concurrency, in particular the executor service technique using a new virtual thread per task executor, where those run in parallel, and then we kind of join the results together. And it also showed how you can nest those computations as well.